Flight 7 of SpaceX's Starship program was an emotional roller coaster, to say the least. At first, we were all elated to witness the almost perfect ignition of all 33 engines, with the rocket slowly ascending into the skies, a truly mesmerizing sight. Even one of the most challenging phases, stage separation, went flawlessly. The Super Heavy booster performed beautifully, returning to the launch tower and being caught by the Mechazilla robotic arms for the second time in SpaceX history. For a moment, it felt like we were witnessing history unfold, but the triumph quickly turned into disaster when the upper stage encountered critical issues shortly after separation. The upper stage was lost, resulting in a catastrophic explosion. Stunning footage of debris streaking across the sky, resembling a space meteor, quickly went viral on social media platforms like Twitter. And of course, when such mishaps occur, the Federal Aviation Administration steps in. The FAA has now initiated an official mishap investigation, a decision that could pose challenges for the timeline of future Starship launches. In this video, we will delve into the details of what happened, the FAA's involvement, and the potential impacts on SpaceX's Starship program. Before we dive deeper, don't forget to subscribe for more updates. The mission started with high expectations, as Starship version 2 featured notable upgrades aimed at improving reliability and performance. One of the mission's highlights was the successful catch of the Super Heavy booster by the Mechazilla robotic arms, a critical step in demonstrating reusability. However, the flight took a dramatic turn during the Starship ascent phase. Shortly after liftoff, issues began to emerge, including a visible hole in the payload compartment and subsequent reports of a fire in the aft section of the spacecraft. SpaceX later confirmed that Starship experienced a rapid, unscheduled disassembly during its ascent. According to Musk, the preliminary analysis pointed to an oxygen-rich liquid methane fuel leak in the cavity above the engine firewall. This leak caused pressure to build beyond the vent system's capacity, leading to the catastrophic failure. SpaceX's flight termination system was activated to ensure safety. In response to the incident, SpaceX is already implementing corrective measures, including enhanced leak detection protocols, fire suppression systems in critical areas, and increased venting capacity. Meanwhile, the FAA's mishap investigation centers on debris dispersion and compliance with safety protocols. While SpaceX maintains that debris fell within the designated hazard warning area, there is uncertainty about whether some fragments drifted outside the expected zone. Starship program has experienced a series of ups and downs, particularly in its interactions with the Federal Aviation Administration. A notable incident occurred on April 20, 2023, when the inaugural flight of Starship ended in an explosion shortly after liftoff. This mishap led the FAA to ground the Starship program, initiating a thorough investigation to identify the causes and necessary corrective actions. The investigation concluded in September 2023, with the FAA outlining 63 corrective measures that SpaceX needed to implement before resuming flights. Following the implementation of these corrective actions, SpaceX resumed its test flights. However, challenges persisted. Some experts believe the FAA might use the recent Starship explosion during Flight 7 to delay SpaceX's upcoming launches, much like they did after the first Starship explosion. Previously, the FAA introduced exemptions for minor anomalies that would not require a full investigation. However, the Flight 7 incident did not qualify under these exemptions. As a result, the investigation could potentially delay SpaceX's timeline, depending on its findings and the corrective actions required. The explosion had immediate repercussions beyond the mission itself. Debris from the disintegrated Starship upper stage fell over the Turks and Caicos Islands, prompting the Federal Aviation Administration to issue temporary flight restrictions in the area. Several commercial flights were diverted or delayed to ensure passenger safety, highlighting the broader implications of such in-flight anomalies. In the aftermath of the incident, SpaceX emphasized its commitment to learning from the test flight. This explosion will definitely not happen in the next launches, because SpaceX has an impressive track record of learning from every test flight. Not a single Starship launch mistake has been repeated so far. They have always improved upon previous designs and systems. Out of all 7 Starship launches conducted so far, it's surprisingly the 5th flight that stands out as the most successful overall. What makes Flight 5 so remarkable is not just its smooth execution, but also how it set a benchmark for what Starship could achieve. Like the 7th flight, Flight 5 also managed to catch the Super Heavy booster with Mechazilla, SpaceX's towering chopstick arms. Where Flight 5 outshines Flight 7 is in the performance of the upper stage. Unlike Flight 7, which ended with the Starship upper stage exploding over the Turks and Caicos Islands, Flight 5 saw the upper stage complete its mission successfully. It followed a flawless trajectory and splashed down in the ocean exactly as planned. Flight 7, however, encountered several significant issues that overshadowed its successes. At T-2 hours, the fueling process began. SpaceX loaded the booster with supercooled liquid oxygen and liquid methane, carefully monitoring the pressurization of the tanks. Engineers also verified the structural integrity of the heat shield tiles on Starship, which had been updated to improve thermal resistance during re-entry. At T-1 hour, the final go-no-go poll was conducted. Each team leader confirmed their system's readiness, from propulsion to guidance and navigation. The results were positive across the board, signaling that the mission was proceeding as planned. The live broadcast began, with SpaceX providing real-time updates and visuals of the rocket on the launch pad. At T-10 minutes, the automated launch sequence was initiated. The launch tower's chopstick arms were retracted to their holding positions, ensuring a clear path for the rocket's ascent. Engineers monitored the countdown closely, watching for any anomalies. At T-2 minutes, the rocket's autonomous systems took over, with the onboard computers finalizing pre-launch diagnostics. At T-10 seconds, the Raptor engines ignited in a staggered sequence, generating a deafening roar and a bright plume of exhaust. The engines ramped up to full power, producing a combined thrust of 16.7 million pounds. At T-0, the clamps holding the Super Heavy booster in place were released, and the rocket began its ascent. The initial phase of the launch was smooth. The Super Heavy booster performed flawlessly, propelling the Starship vehicle into the sky with unprecedented power. The live feed provided breathtaking views of the rocket climbing through the atmosphere, leaving a trail of fire and smoke. The Raptor engines operated at optimal efficiency, with no signs of instability or performance degradation. At T+2 minutes, the rocket passed through max Q, the point of maximum aerodynamic pressure. This milestone was crucial as it demonstrated the structural resilience of both the booster and the spacecraft. At T+3 minutes, the main engine cutoff occurred. The Super Heavy booster shut down its engines, completing its primary role in the mission. Moments later, the booster separated from the Starship spacecraft, which continued its trajectory using its own Raptor engines. The separation was seamless, marking another successful step in the mission. The focus then shifted to the booster's descent and recovery. Equipped with grid fins for stability, the booster began its controlled fall back to Earth. SpaceX's engineers monitored its trajectory closely, making real-time adjustments to ensure it would land precisely on the launch pad. This phase was particularly critical, as it tested the updated guidance systems and the capability of the chopstick arms to catch the booster. Meanwhile, the Starship vehicle continued its flight, carrying 10 Starlink simulators. These mock satellites were designed to replicate the size and weight of actual Starlink satellites, providing valuable data for future deployments. The spacecraft followed a suborbital trajectory, reaching its intended altitude before beginning its descent. At T+6 minutes, the booster approached the launch site. The grid fins worked in tandem with the Raptor engines to align the booster with the designated landing zone. The chopstick arms extended, preparing to catch the massive rocket. The live feed captured the booster's dramatic descent, showcasing the precision of SpaceX's engineering. At T+7 minutes, the booster successfully landed, with the chopstick arms catching it midair and securing it to the launch tower. The booster was then safely lowered onto the pad for post-flight inspections. The Starship vehicle continued its descent, with the upgraded heat shield tiles performing exceptionally well, protecting the spacecraft from the intense heat of re-entry. But just as the mission seemed to be proceeding flawlessly, an unexpected event occurred. At approximately 8.5 minutes into the flight, telemetry from the upper stage was abruptly lost. Moments later, the vehicle exploded, breaking apart during re-entry over the Turks and Caicos Islands. The debris scattered across the sky, creating a spectacle that resembled a meteor shower. Witnesses in the region described the scene as both mesmerizing and unnerving, with fragments of the spacecraft lighting up the night sky as they burned upon re-entry. Initial investigations point to several potential causes for this catastrophic failure. One possible issue may have arisen during the propellant venting process. Toward the end of the burn, excess liquid oxygen is typically vented to maintain balance and stability. A leak or an improper venting sequence in the aft section could have created an unstable environment, potentially leading to a combustion event in an area that should have remained inert. SpaceX, however, remains optimistic. The company has already begun preparing for Flight 8, incorporating data and lessons from Flight 7 to refine both the Starship vehicle and its operational processes. Musk stated that nothing so far suggests pushing the next launch past next month. The Starship Flight 7 began with great promise, but ended in an unexpected and dramatic twist. The mission kicked off at precisely 8 a.m. local time when Booster 14 fired all 33 Raptor engines, lifting Starship 33 from the launch pad at SpaceX's Starbase in Boca Chica, Texas. This marked the first critical milestone, achieving liftoff with flawless engine performance. Over the next 3 minutes, B-14 propelled S-33 to the altitude necessary for the critical hot staging phase, where the Starship upper stage separates from the booster mid-flight and ignites its own engines. At T+3 minutes 45 seconds, hot staging was initiated, and Starship successfully detached from the booster. However, moments later, at approximately T+4, an anomaly occurred. A fuel leak above Starship's methane tank was detected, leading to ignition and a visible fire near the flap hinge area. The fire rapidly escalated, compromising the structural integrity of the spacecraft. By T+4 minutes 10 seconds, the onboard flight termination system was activated as a safety precaution, resulting in a dramatic mid-air explosion. Debris scattered across the Caribbean skies, marking a somber conclusion to a mission filled with both triumphs and challenges. Despite the catastrophic end, the mission offered valuable insights. During its brief ascent, Starship achieved several technical milestones. The booster's Raptor engines set a new record for thrust and operated without issue during the initial ascent. However, subsequent reports suggest that engine-related issues might have played a role in the upper stage's explosion. Specifically, it is possible that residual stresses on the engine components during the hot staging phase could have contributed to the fuel leak or ignited vapors near the methane tank. One potential issue lies in the immense pressure generated by the Raptor engines, which, while delivering unmatched thrust, also push the boundaries of material limits. The full-flow staged combustion cycle used by the Raptors introduces extreme thermal and mechanical stresses, particularly during transitions such as hot staging. If even a minor flaw, such as an undetected crack or irregular weld, occurs in the engine's intricate plumbing, it can cause catastrophic results under these conditions. Additionally, the redesigned fuel feed system tailored for the Raptor vacuum engines may have introduced unforeseen variables. Before the flight, SpaceX has already made several updates to improve the Raptor engines. These changes included increasing the propellant capacity by 25%, which helps the rocket carry more fuel and operate longer. Another upgrade was adding vacuum jacketing to the feed lines to keep the fuel cold and stable. This is particularly important for the vacuum version of the Raptor engine, which is designed to work in space where there is no air pressure. SpaceX also redesigned the fuel feed line system to make sure methane and oxygen flow smoothly to the engines, reducing the chance of blockages or uneven supply. They added new avionics for better control of the engine valves and improved data processing, allowing engineers to monitor the engines in real time and make adjustments if needed. The engines used on Flight 7 were the Raptor 2 models, which are an improved version of the original Raptor engines. Raptor 2 has a simpler design, fewer external parts, and produces up to 230 tons of thrust at sea level. However, even with these improvements, the engines faced extreme conditions during the flight, especially during the hot staging phase when the upper stage separates from the booster. Some reports suggest that these conditions may have contributed to the fuel leak and explosion. SpaceX is already working on the next version, the Raptor 3 engine. Raptor 3 is expected to produce over 280 tons of thrust, and Musk has mentioned that it could reach up to 330 tons in future updates. This engine is being designed to be even simpler and more reliable, with an integrated cooling system instead of external heat shields. Raptor 3 is still in testing and might be used in flights as early as Flight 9 or 10, depending on how development progresses. In the future, SpaceX plans to develop a Raptor 4 engine, which will focus on making the engines last longer and work more efficiently. There is not much detailed information about Raptor 4 yet, but it will likely play a big role in SpaceX's goal of making Starship fully reusable and able to handle many flights to places like Mars. SpaceX is actively preparing for its next Starship test flight, aiming for a launch as early as the first weeks of February 2025. This follows the recent Flight 7 on January 16, 2025, which, despite a successful liftoff and booster recovery, ended with the Starship upper stage exploding over the Caribbean due to a fuel leak. In response to the Flight 7 incident, SpaceX CEO Musk indicated that the company plans to address the issues identified, including implementing fire suppression systems and increasing vent areas to prevent similar occurrences. Musk stated, "Nothing so far suggests pushing next launch past next month." SpaceX aims to conduct up to 20 Starship test flights in 2025, focusing on refining designs, achieving orbital recovery of Starship, and demonstrating orbital refueling capabilities. Meanwhile, Blue Origin has shocked us all with the successful launch of its long-awaited New Glenn rocket. Let's be honest. When they announced the launch date, most of us thought it would just be another delay in a series of postponements. But against all odds, they surprised us with a liftoff that marked a historic moment for the company after years of anticipation. The New Glenn rocket, named after astronaut John Glenn, launched from Cape Canaveral Space Force Station on January 16, 2025. Standing at an impressive 98 meters tall, New Glenn is a heavy-lift launch vehicle designed to compete with SpaceX's Falcon Heavy and Starship in delivering large payloads to various orbits. The rocket's first stage is powered by 7 BE-4 engines, using liquid oxygen and methane propellants, while the second stage is equipped with 2 BE-3U engines optimized for vacuum performance. The mission successfully deployed its payload, the Blue Ring Pathfinder prototype satellite, into medium Earth orbit. This achievement demonstrated that the rocket is capable of performing its primary mission, silencing skeptics who doubted Blue Origin's ability to deliver after years of delays. However, the celebration was tempered by a notable failure. The reusable first-stage booster, designed to return and land on an ocean platform, didn't make it back. After completing its burn, the booster attempted its descent, but telemetry was lost during the critical phase and the landing was unsuccessful. Blue Origin has yet to recover the booster and is conducting an investigation to determine what went wrong. We all witnessed the surprising end of the Starship launch as it exploded mid-air, and viral clips showed debris raining down on an island. Now, an official report sheds light on the reasons behind this incident and its surprising aftermath. Flight 7 of SpaceX's Starship began with high hopes as Booster 14 executed a flawless liftoff and initial ascent. The separation of the Super Heavy booster from the Starship upper stage occurred smoothly, with both components appearing to function as expected at first. This phase demonstrated the success of some of the system upgrades SpaceX implemented for this launch. After separation, the Starship upper stage ignited its engines as planned, heading toward its target trajectory. However, around T+7 minutes and 39 seconds, problems began to emerge. A critical failure occurred when one of the sea-level Raptor engines on the upper stage malfunctioned. Shortly after, at T plus 7 minutes and 52 seconds, a fire was observed in the hinge of the starboard aft flap, signaling further trouble. This fire appeared to be linked to an oxygen leak, which Musk had previously cited as a potential risk factor for the mission. The sequence of events escalated as another sea-level Raptor engine failed at T plus 8 minutes and 2 seconds. A second later, a nearby vacuum Raptor engine also shut down unexpectedly. By T plus 8 minutes and 17 seconds, another vacuum engine had failed, and at T plus 8 minutes and 23 seconds, the final operational sea-level engine shut down, leaving the upper stage with no functional propulsion. The cascading engine failures created a severe thrust imbalance, causing the vehicle to deviate from its intended trajectory. Instead of maintaining stable flight, the upper stage began to rotate uncontrollably. Recognizing the danger, SpaceX activated the flight termination system to safely end the mission, as indicated by the abrupt cessation of altitude and speed data. The dramatic conclusion to the mission immediately sparked concerns about where the debris had landed. Reports suggested that fragments from the spacecraft may have traveled to areas far beyond the designated hazard zones, including the coasts of Puerto Rico and the Dominican Republic. Later investigations confirmed that pieces of the spacecraft had also washed ashore on the Turks and Caicos Islands, intensifying scrutiny over the safety measures and risk assessments for the launch. Initial reports indicated that debris from the Starship explosion may have reached the coasts of Puerto Rico and the Dominican Republic. This was later confirmed when fragments, including heat shield tiles, were found washed ashore on the Turks and Caicos Islands. The event quickly gained widespread attention after dramatic footage of the debris re-entering Earth's atmosphere went viral online. Many described the scenes as resembling a meteor shower, with glowing fragments streaking across the sky in fiery trails, creating a spectacle that looked straight out of a science fiction movie. Early images showed a single heat shield tile discovered on a beach, but as investigations continued, photos began circulating online showing an extensive collection of debris. In one particularly striking image, over 100 pieces of various shapes and sizes were displayed on a table, including at least 2 intact heat shield tiles. These fragments have been a focus of analysis to determine the causes of the mishap. In addition to heat shield tiles, reports also highlighted the presence of metallic debris from Starship S-33 on the islands. This reminds us of the first Starship explosion, where the rocket failed shortly after liftoff, scattering debris across a wide area. Unlike the recent event, the debris from that explosion fell on residential areas near the launch site, causing significant safety concerns. Reports from the time indicated that fragments of the rocket, including metallic shards, landed dangerously close to homes. In some cases, the impact shattered window glass and damaged rooftops, alarming local residents. The FAA grounded SpaceX's Starship program for several months after the first catastrophic explosion that scattered debris near residential areas, causing property damage like shattered windows and damaged rooftops. As a result, the FAA mandated that SpaceX make over 63 specific changes to the Starship system before it could launch again. These changes included redesigning the flight termination system to ensure debris would be minimized in future failures, and expanding hazard zones to keep debris away from populated areas. Given the serious consequences SpaceX faced after past Starship incidents, many are now wondering how the FAA is reacting to the recent Flight 7 explosion and whether the Starship program will be grounded again. The FAA has already launched a formal mishap investigation into the incident and has imposed strict conditions on SpaceX moving forward. On January 16th, the FAA announced that SpaceX is required to identify the root cause of the explosion and implement corrective measures before any future Starship flights can occur. Unlike previous investigations, this time the FAA is particularly focused on understanding how debris from the spacecraft reached populated areas like the Turks and Caicos Islands. Although Musk has publicly stated that he hopes to proceed with Flight 8 as early as February, this timeline depends entirely on how quickly SpaceX can satisfy the FAA's demands. Over the coming weeks, SpaceX must map debris locations, provide detailed reports on what went wrong, and propose design changes to address the underlying issues. The FAA will evaluate these changes before deciding whether to lift the suspension on Starship test flights. If SpaceX meets all the requirements set by the Federal Aviation Administration, Starship's Flight 8 is expected to proceed as planned. The upcoming test flight is anticipated to utilize Ship 34 and Booster 15, marking the second flight of a Block 2 ship. Flight 8 aims to build upon previous test flights by achieving a fully successful mission profile, including stage separation, orbital insertion, and recovery operations. Notably, this flight is expected to attempt the first catch of the Starship upper stage. Musk has expressed optimism, suggesting that the next launch could occur as early as next month, stating, "Nothing so far suggests pushing next launch past next month." In preparation for Flight 8, SpaceX is expected to implement corrective actions based on the findings of the FAA's investigation. The upcoming flight aims to test a more powerful version of the Starship and Super Heavy rocket, referred to as Starship 3, which is projected to double the thrust of the upper stage and increase the booster's thrust from approximately 74 meganewtons to about 100 meganewtons. In preparation for Flight 8, SpaceX has conducted extensive testing on the prototypes. Ship 34 and Booster 15 have undergone rigorous evaluations, including static fire tests and structural assessments. One of the key differences in these prototypes is the implementation of design modifications to enhance reliability and safety. These changes are informed by the lessons learned from previous test flights, including adjustments to engine configurations, structural reinforcements, and updates to flight software. The goal is to incrementally improve the Starship system's performance and pave the way for future operational missions. Looking ahead to 2025, SpaceX has ambitious plans to increase the frequency of Starship launches. The FAA has released a draft environmental assessment proposing an increase in the number of annual Starship liftoffs from the current 5 to 25. This adjustment would allow SpaceX to conduct more frequent launches without seeking separate licenses for each flight, streamlining the approval process. That's all for today's video. Thanks for watching, and we hope to see you in the next one.